We are now technically done with the self-attention mechanism, the one that we implemented in the previous section, the multi-head attention mechanism. But I wanted to show you one more way to implement multi-head attention a bit more efficiently. So previously, one downside of the implementation was that we were stacking multiple attention modules. And then when we were calling them in the forward method, that was a sequential call here. So we had to iterate through those sequentially. I mean, not us, but the computer. And this is not very efficient for, let's say, GPUs or even CPUs when we train this. Because technically we could execute the calculation in parallel, parallelizing things under the hood using, for example, matrix multiplication, because for loops are always a bit slow in Python because one for loop has to wait for the other for loop to finish. But since these attention heads all operate independently of each other, there's no need for one to wait for the other. So I'm going to show you an alternative implementation, and this is a bit technical. It's a lot of code. It took me a long time to write this code. I will walk through this a bit, but I didn't want to retype everything because it's easy to make mistakes in certain cases. But I will walk you through the big picture idea here. So here, again, similar to before, we get the context vectors of shape 1, 2, 3, 4, 5, 6, 6 times 4. This is similar to what we have here. The values are a bit different because we use a different initialization here. But we'll get to that in a moment. But mathematically, the operations in there, they are giving us the same results. So you could technically take either one of them, plug them into an LLM, and then train them in the LLM. And when we get to chapter 5, maybe as an exercise, you can swap out the attention mechanisms and see that the model will train with either one of them. It's just that this one is faster during the training. So what is happening here? So let me go through this step by step. So what's happening here is we are still initializing the same variables as before. And then we have this assertion here. We are saying the output dimension, the dimension we have here, has to be divisible by the number of heads. So if we have output dimension 4 and we divide it by the number of heads, let's say 2, this should be not giving you any remainder. So because this determines the dimension of each head. So here, if this is 4, this is 2, we have a 2-dimensional head dimension. And the head dimension, you can think of it as the dimension also of the context vector before we concatenate them. Now, maybe let's make, or let's just keep it like it is for now. And going a bit further down here. Now what we have is we have a query, a key, and a value like we had before, but they are bigger now. So before we had d out of 2, so d out was equaling 2. Now we have it set down here to 4, which means these are bigger weight matrices compared to our causal attention module before. So we are just, instead of concatenating multiple causal attention mechanisms, we are just using a bigger weight matrix here. I think I have a figure on that somewhere here. I can show you maybe better what I mean. So before, in the previous section, what we did is this one. So we had the inputs, and then we had a stack of 2 weight matrices. Here I'm only showing you the queries, but the same would apply to the keys and values. And then we multiplied the inputs with the query and got the queries here. And then we did the second multiplication and got the second set of queries. And we did the same for the keys and the values. We got 2 attention matrices and 2 context vectors, and we concatenated them. And this is a a reasonable thing to do, a valid thing to do. But this is inefficient unless we do this at the same time. So in our previous implementation, we had the Python for loop where this was inefficient because it happened sequentially. So it was first doing this and then was doing this. And now one way we can do both of them at once is by combining those into one weight matrix. So it's a linear algebra concept, but if you concatenate those weight matrices to one bigger weight matrix, like here, then what you could do is you can do the multiplication between the inputs in the weight matrix here, and then you get the queries out here. And then when you split those, you get, similar to above here, 2 query sets. And what's happening here is mathematically the equivalent thing. You get exactly the same values, but this one is cheaper because you can do this in one go. So the way it's implemented, this can be one matrix multiplication, and splitting is incredibly cheap in Python and PyTorch. This one is expensive before because we had a for loop doing them separately. So that's the whole idea between what I'm showing you here, that we have now these bigger matrices, and then here we compute the keys, queries, and so forth. So this one here that you're seeing corresponds now to this bigger queries. And then what you are seeing here is the splitting. So here we are performing this splitting operation, and we are going to use the view. It's just reshaping it. And so we are splitting it by introducing the number of heads. So before, the input dimension of each of these is the batch size, the number of tokens, and the output embedding size. So for example, this would be 2 if we consider our batch, 6 tokens, so 2 times 6, and then 4, 2, 6, 4. And then we are going to split this into 2, 6, 2, and 2. So we are splitting this dimension, the 4, into 2 and 2. And this is why I have this one here, because it has to be divisible, right? So we want this head dimension to be nicely divisible so that we can split this one up into this one. Okay, and this is all we do. And then, we similarly compute the attention scores, the mask, the weights, get the context vectors, and so forth. There's one more thing though here, the contiguous view. This is where we are combining the context vectors. So we are now going from number of heads, head dim. So we do everything separately here. So we have this heads, num heads and head dim. And now we are combining it again into the out so that we get the concatenated context vector. So if I go back up again, this is essentially performing this concatenation here again. And why am I using contiguous in view? This is just because we kind of fractured the memory at some point. So in PyTorch, the tensors are held in memory, and with all our operations, they got a bit fractured, and it didn't allow me to do the view without the contiguous. It was complaining that things are scattered in memory and it's inefficient. And here we are just reorganizing things internally in the computer memory, just for efficiency reasons. And by the way, you don't even have to write it like this. You could also just write, instead of this, you could just write reshape. This doesn't need the contiguous. However, since I used in this book view before and I introduced view in the appendix, I didn't want to overcomplicate things and I was sticking with view. But technically, view and reshape are similar in PyTorch, except reshape creates a copy, and this one does an in-place modification. So, or it doesn't copy anything in memory. So in this case, we need to manually rearrange the memory. But here, by the way, this is a technical detail. You don't really have to think about it too hard. Just maybe consider reshape here. It doesn't really matter. And so that is what is happening. So let's just see, make sure that it still works. So yeah, this works. And by the way, I can also show you what I meant. It's not super interesting, but if I do this, it will complain about this. So we can use either reshape or this contiguous, whatever you prefer. And that is what I wanted to say here. And why 4? This is arbitrary. Technically, here it happened to be like that because each of them, we had 2 heads and each of them had a dimension of 4. But now with our new modification, we are actually even more flexible. So we can also still have an output dimension of 2 if we want to. So that would be also more flexible. So we can control even the output size more easily. And one more thing I should say, I was talking about efficiency here. This is one way to implement this more efficiently. But if you are interested in more bonus material, I know this is very technical now, so You can feel free to stop this video and go to the next chapter if you want to. But if you're curious, I implemented many different types of attention mechanisms and compared them in terms of the efficiency. So let me just go back. Maybe I've clicked on the wrong thing. If I scroll down, chapter 3, comparing efficient multi-head attention implementations here. There we go. So here, what I have is I have a notebook where I compare different attention mechanisms. This is based on PyTorch 2.5. Right now, PyTorch 2.6 is out, and it becomes actually even easier. So here I have, for example, the causal attention multi-head attention wrapper that we implemented first. So this would be corresponding to this one. Next, I have what we've just implemented, the more efficient version. This is what we've just implemented. Then I have another way of implementing it here with combined QKV matrices. This was suggested by a reader. And here, what we are doing is instead of having a separate value key and query matrix, we only have one matrix here. So it's a 3 times as large matrix. So instead of having, let me scroll down, oops, here. Instead of having them separate, QKV, we have now one that is essentially 3 times the size. Oops. And then similar to what we've done before, we are going to break it down later after the matrix multiplication. It's a similar concept to what we have done here and then breaking it down here, where we have multiplication with a bigger matrix and then we split it. But now we go even one level further, where instead of having 3 different matrices, we have one big matrix. So yeah, that is what you're seeing here. Then I have, just for fun, because I like Einstein summation, I have an implementation using Einstein summation. It's just a different notation here. So maybe don't worry about it too hard. It's just like a little, little thing I had fun with. Then here is PyTorch's scaled dot product attention. So this is a PyTorch official implementation of the attention mechanism. So I'm using it right here. So instead of me performing the attention score calculation and so forth, so this is replacing the part down here. So here we are letting PyTorch take care of the attention score and weight computation. Then there's another one. So this one, by default, if you have a GPU that supports multi-head attention, flash attention, this will use flash attention, which is an implementation that is more efficient. Here, I have another implementation doing the same thing for benchmark purposes without flash attention. There is another way to implement this. It's a class in PyTorch, the multi-head attention class. So I don't want to go into too much detail here because it might be boring by now. Yet another implementation, and there's also PyTorch's new flex attention. And so you've seen there are 9 different ways of implementing the self attention mechanism in PyTorch. They should be all mathematically equivalent. And then I benchmarked them. So here first on a CPU. So you can see causal attention is slightly slower than the other one, the one we implemented. For some reason, the combined QKV is slower, but we will revisit this in a few moments. My Einstein summation is actually the slowest, but it's fun. And then you can see the PyTorch implementations are actually faster, except for this multi-head attention class. So this was on CPU. I did the same benchmarks on GPU. Let me just scroll down to visualizations here that I have. So you can see all of them compared to each other, 9 different attention mechanisms. I see this should be a 9 here. And so what you can see is that the fastest one is using multi-head attention with the PyTorch scaled dot product function. If it's using flash attention, and you can see this one is the slowest flex attention. We will revisit this in a few moments. So we can also see the sequential attention class that we implemented in the previous video is slower than this more efficient version that we just implemented in this section. And the QKV combination is slightly slower than this. So this is actually a quite nice implementation we have here, given that it's a from scratch implementation. Of course, PyTorch's native one is faster because it's more optimized, but this is actually not too bad, what we have so far. And then I've done the same thing with both a forward and a backward pass. If a backward pass is a new term for you, this will be explained more in chapter 5 when we are training the neural network. So here, more benchmarking, similar relationship between the numbers. And then I also added compilation. So Torch compile is a nice function to make things faster, to compile a static graph. And here, what we can see is nice in the compiled case, the QKV combination is actually slightly faster than ours here, but you can see ours is actually quite nice. It has not a big disadvantage compared to PyTorch's native one anymore. It's slightly slower, but the compilation helps optimizing this. And you can also see flex attention is now fast. So for flex attention, you definitely need to use compile because otherwise it's very slow. So it's meant to be compiled. But yeah, you can see overall our implementation here, what we have, this MHA code, which is what we have here, is not too bad after all. And this is really a nice readable from scratch implementation where we can really understand what's going on. And yeah, so with that, this chapter was covering the self-attention mechanism. In the next chapter, we will be putting together all the remaining blocks. So we will be coding all the other parts of the LLM. And then in chapter 5, we will be actually training that.
Get this book at manning.com.